Today, we are going to talk about emptiness, about the kind of emptiness that could swallow every star you have ever seen in the night sky and still have room left over. An emptiness so vast that if you spent your entire life traveling through it at the speed of light, you would die long before you reach the other side. These places exist. They are real. They are scattered across our universe in numbers that are difficult to fully absorb, and they take up far more of the cosmos than everything else combined, more than all the stars, all the galaxies, all the glittering filament of matter that we tend to think of when we picture space. Most of the universe, it turns out, is not the beautiful spiral galaxies in astronomy photographs. Most of the universe is this: silence, space, nothing, or so it appears. Because over the last few decades, scientists have been looking more carefully into these vast hollow places, and what they're finding there is quietly rewriting some of the most fundamental ideas we have about how the universe works. These great voids are not simply empty corners of an otherwise full cosmos. They are active participants in the story of everything. They shape how galaxies grow. They may be distorting our measurements of the universe's expansion rate, and some researchers are now beginning to suggest that the emptiness itself carries energy, a faint, persistent hum of something where there should be nothing at all. Tonight, we're going to go there. We're going to start with a discovery that happened almost by accident in 1981, when a group of astronomers pointed their instruments at a stretch of sky in the constellation Boötes and found, to their complete bewilderment, that something was missing. Then we will pull back and see the full picture, a cosmic architecture so strange and so beautiful that it has been compared to soap bubbles, to foam, to the inside of a sponge, and even to the network of a slime mold. And finally, we will ask a question that is still open. What does all this emptiness actually mean? What is it telling us about where we came from and where we are going? Take a breath. Let's begin. The accidental discovery of nothing. It was 1981, and Robert Kirshner was not looking for a hole in the universe. He was a young astronomer at the Harvard-Smithsonian Center for Astrophysics, and he was doing something that sounds almost routine: mapping galaxies. Together with his colleagues Augustus Oemler, Paul Schechter, and Stephen Schechtman, he was taking spectra of distant galaxies in several small patches of sky, measuring their redshifts to figure out how far away they were. Redshift is the stretching of light that happens when a source is moving away from you. The more a galaxy's light is shifted toward the red end of the spectrum, the faster it is receding, and therefore the farther away it is. By cataloging these redshifts, the team was building a rough three-dimensional map of a small slice of the cosmos. The work was technical. The results were supposed to be statistical. Nobody expected anything surprising. But then the data came back, and something was wrong. In 3 separate fields of sky, fields separated by angles of roughly 35 degrees, which is a substantial portion of the sky, the team found an identical gap between approximately 12,000 and 18,000 kilometers per second of recession velocity. There were almost no galaxies, just blank space. In a paper published in 1986, they wrote, "We discovered that the redshift distributions in each of the 3 northern fields showed an identical gap. Because these fields were separated by such large angles, this suggested the existence of a large void in the galaxy distribution of at least comparable angular diameter." They then added a line that has stayed with astronomers ever since. They noted that the low density of this region was, quote, "of high statistical significance and does not appear easily reconcilable with any of the popular models for growth of structure in the universe." In other words, we do not know what to make of this. The void they found was located in the direction of the constellation Boötes, the herdsman, a faint kite-shaped figure most visible in spring and summer nights. The feature quickly became known as a Boötes Void. Some people, with a dry astronomer's humor, called it something else: the Great Nothing. It is one of the largest known voids in the observable universe. Its diameter spans approximately 330 million light-years. To get a feel for what that number actually means, consider this. Our nearest large galactic neighbor, the Andromeda Galaxy, is about 2.5 million light-years away. The Boötes Void is more than 100 times wider than that distance. If you were to stand on the edge of the void and attempt to cross it in a spacecraft traveling at the speed of light, the absolute maximum speed anything can move in this universe, your journey would take 330 million years. You would cross roughly the same span of time that separates us from the Carboniferous period on Earth, when the first reptiles were just learning to lay eggs on dry land. And the void would not care. It would just keep sitting there, vast and quiet, while you crossed it. Now here's what makes the Boötes Void remarkable even beyond its sheer scale. In a typical region of space that size, a sphere 330 million light-years across, astronomers would expect to find somewhere in the neighborhood of 2,000 galaxies, based on the average density of the observable universe. 2,000 islands of stars, each containing billions of suns, each with their own planets and moons and the potential for everything we know. When researchers carefully surveyed the interior of Boötes Void, they found approximately 60 galaxies in a region that should hold 2,000. That is like empty an auditorium of 2,000 people, keeping 60 of them inside, switching off the lights, and then trying to claim the building is occupied. Technically true, profoundly misleading. The astronomer Greg Aldring, reflecting on the scale of the discovery, said something that has been quoted many times since, because it captures the strangeness so well. He said, "If the Milky Way had been in the center of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. Think about that for a moment. Everything humanity ever looked at in the night sky, all the philosophical weight placed on those pinpoints of light, all the stories and myths and the hard-won science, it all required that we live somewhere near other galaxies. If we had been born in the Boötes Void, in the deepest part of that hollow sphere, the sky at night would have looked almost exactly the same from the outside. Stars within our own galaxy scattered across the darkness. But the idea that there were other galaxies, other structures, an entire cosmic web of matter beyond our island of stars, that would have been unknowable for most of human history. The extragalactic universe would have been invisible. We would have thought we were alone, not just on Earth, but in all of space. What is a void, actually, before we go deeper? And we're going to go much deeper. It is worth being precise about what we mean when we say void. In everyday speech, a void suggests perfect emptiness. Zero matter, zero light, zero anything. But the universe does not really operate in absolutes like that. The Boötes Void, the great nothing, the supervoids and cosmic holes we're going to discuss tonight, none of them are perfectly empty. They are regions of dramatically below average density. Regions where matter has been pulled away, thinned out, redistributed to surrounding structures over billions of years, until what remains is a kind of sparse fog compared to the dense walls and filaments just outside. The 60 galaxies still inside the Boötes Void are real. They are there, but they are spread across an almost incomprehensible volume, isolated from one another in ways that galaxies in denser regions of space simply are not. Research has shown that galaxies found inside voids tend to have distinct characteristics compared to their cousins in filaments and clusters. They are often bluer, more actively forming new stars, and host younger stellar populations. In the relative isolation of a void, with less gravitational interference from neighbors, a galaxy evolves differently, more slowly, more quietly. It is a bit like the difference between a city and a village. The same kind of people, but shaped by very different environments. Now, the deeper question, why do voids exist at all? The answer begins at the very beginning. Not in a metaphorical sense, but literally. It begins in the first fractions of a second after the Big Bang, in the quantum noise of the earliest universe. When the universe was born, the matter inside it was not perfectly uniform. The physics of quantum mechanics essentially guaranteed a kind of cosmic static, tiny, random fluctuations in density distributed throughout the primordial soup. Some regions were infinitesimally denser than average. Others were infinitesimally less dense. The differences were almost nothing, fluctuations of roughly 1 part in 100,000. But gravity is patient, and gravity is relentless. Over millions, then billions of years, gravity amplified those tiny differences. The slightly denser regions began to pull in more matter from their surroundings. As they gained mass, their gravitational pull increased, which pulled in still more matter, which increased their gravity further. A positive feedback loop running for billions of years. Meanwhile, the regions that start out slightly less dense began to be emptied. Their matter pulled away toward the denser neighborhoods. As they lost matter, their gravitational pull weakened, which made it easier for more matter to leave. This is the same process described by the Zeldovich approximation, a framework developed by Soviet physicist Yakov Zeldovich in 1970 that predicted, decades before we could observe it directly, that matter would collapse not into spheres but into sheets, then filaments, then dense nodes at intersections, and that the spaces in between would be stretched into enormous empty regions. He was right. The structure of the universe looks almost exactly like what he predicted. What you get over cosmic time is a structure that has been compared to a sponge, to a foam of soap bubbles, or, in a more evocative description used by several researchers, to the mycelium network of a fungus. Dense threads of galaxies called filaments, running for hundreds of millions of light years. Flat sheets where filaments meet, hosting superclusters of thousands of galaxies. And at the intersections of the largest filaments, enormous nodes, the most massive bound objects in the universe, galaxy clusters that contain hundreds or thousands of individual galaxies, all caught in each other's gravitational embrace. Between all of this, the voids, the places matter left behind. Astronomers call this structure the cosmic web, and it is, by most measures, the largest coherent structure in existence. Every galaxy we have ever photographed, every nebula, every star, every system of planets, including our own, all of it is threaded along the filaments of this web. And surrounding all of it, making up the vast majority of the universe's total volume, are the voids. Current estimates suggest that voids account for somewhere between 70 and 80% of the total volume of the observable universe. The dense structures we tend to focus on, the galaxies, the clusters, the beautiful cosmic architecture, are the minority. They are the walls of the sponge. The voids are the holes. The scale problem. One of the persistent difficulties in thinking about cosmic voids is that human intuition was not built for these scales. Our brains evolved to navigate a world measured in meters and kilometers. We are reasonably good at imagining a few hundred kilometers, passable at imagining a few thousand. Beyond that, our intuition started to fail quietly, without us noticing. So let's try a series of comparisons. Not because they will make the numbers feel comfortable, they will not, but because the discomfort itself is informative. The distance from Earth to the Moon is about 384,000 kilometers. Light travels that distance in just over a second. The distance from Earth to the Sun, what astronomers call one astronomical unit, is about 150 million kilometers. Light crosses it in about 8 minutes. The nearest star beyond our Sun, Proxima Centauri, is about 4.2 light years away. To put that in terms of our moon comparison, if the Earth-Moon distance were 1 centimeter, Proxima Centauri would be about 110 kilometers away. Our galaxy, the Milky Way, is roughly 100,000 light years across. In the same comparison, the Milky Way would be about 2.6 million kilometers wide, roughly 7 times the distance from Earth to the Moon. The Andromeda Galaxy, our nearest large neighbor, sits about 2.5 million light years from us. Now, the Boötes Void is 330 million light years across. On our scale comparison, where the Earth-Moon distance is 1 centimeter, the Boötes Void would be approximately 8.6 billion kilometers wide, about the same as the diameter of Neptune's orbit around the Sun. The void is, in relative terms, solar system scale, and that is just one void in one corner of the observable universe. What we are doing when we study cosmic voids is not just measuring empty space. We are measuring the skeleton of the universe itself, the negative space that defines the shape of everything that exists, inside the great nothing. When astronomers first characterized the Boötes Void, many assumed it was a genuinely featureless expanse, a simple absence of structure. But as surveying technology improved and more galaxies inside the void were cataloged, something interesting emerged. The roughly 60 galaxies found inside the Boötes Void are not randomly scattered throughout the volume. They tend to cluster along a rough cylindrical or tube-shaped region running through the middle of the void. This observation led to one of the leading hypotheses for how the Boötes Void formed in the first place. The hypothesis, and it remains a hypothesis, not a confirmed fact, is that the Boötes Void did not begin as a single enormous void. Instead, it may have been born as a collection of smaller voids that gradually merged together over billions of years, much the way soap bubbles coalesce when you press them together. Each smaller void would have had its own shell of galaxies at its edges. As the voids merged, their outer shells would have been swept together, eventually concentrating into the filament of galaxies we now observe running through the interior. It is an elegant picture. It is consistent with what the Lambda CDM model, the current standard model of cosmology, predicts about how structure forms over time, and it would explain why the interior of the void is not completely empty. It contains a residue of the smaller structures that were dissolved into it. But let us be careful here. This is a prevailing hypothesis. It fits the data. It does not conflict with the standard model. But the Boötes Void has not been fully mapped. The number of confirmed galaxies inside it is still modest, and the exact mechanism of its formation remains an open area of research. What we can say with confidence is this. The Boötes Void is roughly spherical, approximately 330 million light-years across, set at about 700 million light-years from Earth, and it is one of the largest known underdense regions in the observable universe. Its existence is consistent with our current understanding of cosmological structure formation. It is not a mystery in the sense of being inexplicable, but it remains a remarkable object because its sheer scale pushed the boundaries of what astronomers in 1981 thought was possible. The cosmic foam. Now let us zoom out. The Boötes Void is, in a sense, a celebrity, the most famous void, the most studied, the one that appears in every popular article on the subject. But it is not alone, not remotely, the observable universe, the sphere of space from which light has had enough time to reach us since the Big Bang, is roughly 93 billion light-years in diameter. Within that volume, there are hundreds of billions of galaxies, and threading through all of them, connecting them and separating them, is the cosmic web. Galaxy surveys conducted over the last few decades, especially the Sloan Digital Sky Survey, which has mapped millions of galaxies in 3 dimensions, have revealed the full texture of this web. When you look at these maps, what you see is not a random scatter of galaxies. You see structure, long, bright filaments of galaxies, curving through space like luminous rivers, flat walls where filaments intersect, dense nodes blazing with light where multiple filaments meet, and between them all the voids, round, dark, bubble-like regions with filaments curve around empty space. Some researchers have noted that the cosmic web bears a striking resemblance to the neural networks of the human brain, dense nodes connected by thin strands, surrounding empty space. This similarity has been noted in peer-reviewed literature, though it should be understood as a structural analogy, not a claim that the universe is in any sense conscious or that the resemblance has a deeper meaning. It is one of those coincidences that the universe produces occasionally, a reminder that similar physical processes, in this case, the optimization of network structures under constraints, can produce similar-looking architectures even in wildly different contexts. Other researchers have compared the cosmic web to the growth pattern of Physarum polycephalum, a type of slime mold, which also forms an optimized network of dense strands surrounding empty regions. Japanese scientist Atsushi Taro and his colleagues showed in 2010 that the slime mold's growth patterns could actually be used as a mathematical model for identifying cosmic filaments, not because the slime mold is connected to the cosmos in any mystical sense, but because both systems are solving similar optimization problems using the tools available to them. The cosmic web is the universe's solution to the problem of gravity. Given a uniform distribution of matter with tiny random fluctuations, allowed to evolve under the laws of physics for 13.8 billion years. This is what you get. Not a smooth, featureless expanse. Not a random scattering of galaxies. A web. And most of the web, most of its volume, is the space inside the bubbles. Voids occupy most of the universe. This is a point worth sitting with for a moment, because it tends to get lost in the usual astronomy narratives. When we talk about the universe, we tend to talk about objects, galaxies, stars, black holes, nebulae, the exciting, luminous, energetic things that telescopes were built to observe. And there is nothing wrong with that. Those objects are extraordinary, but by volume, they represent a tiny fraction of what exists. The filaments and walls and clusters of the cosmic web, everything containing most of the visible matter in the universe, occupies somewhere between 20 and 30% of its total volume. The remaining 70 to 80% is voids. The universe is mostly empty. Not empty in the simple vacuum sense. We will come back to what empty actually means at the quantum level, and it turns out to be something stranger than you might expect. But empty in the galaxy sense. Most of the volume of the universe contains very few galaxies, very little ordinary matter, very little of what we traditionally think of as stuff. The cosmic web is like a very thin soap bubble foam. Enormous bubbles with incredibly thin walls. If you were to randomly teleport yourself to a random location in the observable universe, the odds are heavily in favor of you finding yourself inside a void, floating in the relative darkness between filaments, with the nearest concentration of galaxies somewhere in the distance. This statistical reality is what makes voids not just interesting cosmic curiosities, but genuinely important scientific tools. The size, shape, and distribution of voids carry encoded information about the universe's history and content. The rate at which voids grow tells astronomers about the balance between gravity, which tend to pull matter together, and expansion of space, which tend to push everything apart. The profile of a void's edge, the way galaxy density transitions from sparse to dense as you approach a filament, reflects the physics of structure formation in ways that complement what we learn from galaxies themselves. In recent years, a growing body of research has begun treating voids as one of the best laboratories we have for probing dark energy, the mysterious component that appears to be driving the accelerating expansion of the universe, as well as the properties of dark matter and the mass of neutrinos. Voids are sensitive to these forces in ways that complement what we learn from the denser structures, and in some respects they provide cleaner signals. Because the physics inside a void is simpler than the physics inside a dense cluster, the problem nobody expected to find. So far in this story, voids are the passive sculptors of cosmic architecture. The spaces left behind when matter flows away, shaped by gravity and the expansion of space, useful as scientific probes, but not particularly surprising in themselves. Then came 2013, and the Boötes Void, impressive as it was, started to look relatively modest. That year, a team of astronomers led by Ryan Keenan, Amy Barger, and Lennox Cowie published a paper describing an underdense region centered approximately on our own galaxy, the Milky Way. Their analysis of galaxy counts and the distribution of light in the local universe suggested that we live not in a typical patch of the cosmic web, but inside an enormous void, a region roughly 2 billion light-years in diameter, with matter density somewhere between 15 and 50% lower than the cosmic average. This feature became known as the KBC Void, named for its 3 discoverers. Some call it the local hole. If confirmed, it is roughly 6 times the diameter of the Boötes Void, making it one of the largest known underdense regions in the observable universe. And it contains at its approximate center our home galaxy and everything we have ever known. The KBC Void remains scientifically contested. Its existence is not confirmed in the same way that the Boötes Void is confirmed. Some analyses support a significant local underdensity. Others suggest the effect is smaller than Keenan and colleagues initially reported. The scientific literature on this question is active and genuinely unsettled. What most researchers agree on is that there is some degree of local underdensity, that our corner of the universe is, in some sense, emptier than average. The exact size and depth of that underdensity is still being measured and debated. But here is why this matters beyond the abstract pleasure of knowing where we live. If we are indeed sitting inside a large cosmic void, it could have a concrete, measurable consequence for one of the biggest ongoing disputes in modern cosmology. This dispute goes by the name of the Hubble tension. The Hubble constant, named for Edwin Hubble, the astronomer who first established that the universe is expanding, is a number that describes the rate of that expansion. It tells you how fast a galaxy at a given distance from us appears to be receding. The problem is that when astronomers measure the Hubble constant using observations of a nearby universe, supernovae, Cepheid variable stars, galaxy distances, they consistently get a slightly different answer than when they calculate from observations of the early universe, specifically from the cosmic microwave background radiation, the faint afterglow of the Big Bang. The discrepancy is about 10%. That might not sound like a lot, but in physics terms, it is enormous. Both measurements are made with extraordinary precision, and both sides have checked their work repeatedly. The disagreement has been called one of the most significant open problems in modern cosmology. One proposed explanation is the local void hypothesis. The reasoning goes like this. If we are sitting inside a region of space that is less dense than average, the gravitational pull from surrounding structures would cause matter inside the void, including us, to drift outward toward the walls. This outward drift would add to the apparent recession speed of nearby galaxies as measured from Earth, making the local expansion rate appear faster than the global average. In 2025, astronomers Indin Obanik and Vasilios Kaliatsidis published an analysis specifically testing this hypothesis using baryon acoustic oscillation measurements, standard rulers embedded in the distribution of galaxies, and found that a local void is a plausible contributor to the tension. Bannock has previously calculated that the KBC void alone could account for a local Hubble constant roughly 11% higher than the global average, precisely the magnitude of the discrepancy. This is a hypothesis. It is not the only proposed explanation for the Hubble tension, and the scientific community has not reached consensus on whether the local void is the answer. Other proposed solutions involve modifications to dark energy, the possibility of early dark energy, new physics that affected the universe before recombination, and more. But the local void hypothesis is taken seriously. It is being actively tested, and it illustrates something important. Voids are not just empty corners. They can shape the physics we measure from inside them. If we live in one, we have been measuring the universe from inside an unusual place all along. What the voids smell like. There is a question that almost everyone thinks about when they first learn about cosmic voids, even if they do not articulate it precisely. What would it actually be like to be inside one? Not as a scientist, measuring redshifts and galaxy counts, but as a traveler, as a conscious being, floating somewhere in the middle of the Boötes Void, looking around. The honest answer involves some mathematics, but let us try build an intuitive picture. First, the obvious. The void is not dark in the way a room is dark when you turn off the light. Space is never truly dark in that sense. Even the deepest void is filled with the cosmic microwave background radiation, a faint, diffuse glow of microwave wavelength light that fills the entire universe uniformly, the remnant of the hot plasma of the early cosmos. You cannot see it with your eyes, but it is there, washing over you from every direction, a 13.8 billion year old echo of the Big Bang. Beyond that, some photons from the distant galaxies outside the void would still reach you. The void is large enough that those galaxies would be at cosmological distances, hundreds of millions of light years away, but they would not be entirely invisible. A sufficiently sensitive detector could still find them. But here is what would be different. The sky, as seen from deep inside the Boötes Void, would be much emptier than what we see from Earth. The filaments and walls of galaxies visible to us, the faint smudges through a telescope that tell us the cosmic web is real, would appear far more distant, crowded together in certain directions that correspond to the edges of the void. The interior of the void would have very little of that. A few dozen isolated galaxies, each the size of a faint smudge in a large telescope, separated from each other by tens of millions of light years of empty space. Greg Aldrin's observation was exactly right. If an intelligent civilization had evolved inside the Boötes Void, they would have seen no external galaxies with the naked eye or even with modest instruments. The few dozen galaxies inside the void would have been visible, but they would have been extraordinarily distant by the standards of what we can observe from Earth. The idea that there were billions more galaxies beyond the void's walls, that the universe had a large-scale structure, that the cosmic web existed, all of that would have required either much more powerful telescopes or a great deal of theoretical cleverness, or both. This is not purely a thought experiment. It is a reminder that our understanding of the universe depends heavily on our location within it. We have been relatively lucky living in a moderately dense filament where the structure around us is accessible to observation. The universe has not always placed observers in such convenient spots, assuming, of course, that there are other observers elsewhere, which is itself a question we cannot currently answer. The quantum hum of the void. Now comes the part that tends to surprise people because it sits at the intersection of cosmology and fundamental physics, and the answer is genuinely strange. We said earlier that voids are regions of below-average density. They contain fewer galaxies, less matter, less of everything we typically catalog. But what about the things we do not catalog? What about the properties of space itself? This is where modern physics forces us to revise the intuitive picture of emptiness. In quantum field theory, the framework that describes all known fundamental particles and forces, there is no such thing as truly empty space. Even a perfect vacuum, a region with zero particles of any kind, still contains something. The quantum vacuum itself, a state of minimum energy that is not actually zero. Virtual particles constantly flicker into and out of existence for tiny fractions of a second. Fields that permeate all of space have a ground state energy that cannot be reduced to nothing. This is not philosophy. It has measurable consequences. The Casimir effect, for instance, the small attractive force measured between two closely spaced metal plates in a vacuum, arises directly from the quantum properties of empty space. In a recent study from 2025, researchers highlighted something directly relevant to cosmic voids. Even in these vast empty regions, stripped of most galaxies, most ordinary matter, most dark matter, the fundamental quantum fields that fill all of space remain intact, carry what physicists call vacuum energy or zero-point energy. In the dense environments of galaxy clusters, this energy is overwhelmed by matter and radiation. But in the deep emptiness of a cosmic void, matter becomes so sparse that the vacuum energy begins to dominate the local energy budget. This connects to dark energy, the component of the universe that appears to be driving its accelerating expansion. One candidate explanation for dark energy is precisely this vacuum energy, this irreducible baseline energy of empty space. If that explanation is correct, then the voids are not just passive containers of absence. They are the regions with the most fundamental energy in the universe. The energy of the vacuum itself is most clearly expressed because there is so little else to compete with it. Dark energy is responsible for roughly 68% of the total energy content of the universe, according to current measurements. Ordinary matter, everything made of atoms, including every galaxy, every star, every planet, accounts for only about 5%. Dark matter, which does not emit or absorb light, but has gravitational effects we can measure, accounts for roughly 27%. The voids, with their dominant vacuum energy and their near absence of ordinary matter, are in a very real sense the regions where dark energy most directly governs the local physics. They are the face of the universe's dominant component. In December 2024, a paper published in the journal Monthly Notices of the Royal Astronomical Society proposed an even more provocative idea, that the acceleration of the universe's expansion might not require dark energy as a separate physical ingredient at all. Instead, the researchers suggested the large-scale structure of the cosmos, specifically the arrangement of voids and filaments, might create an apparent acceleration that is, in a sense, an illusion generated by our position within that structure. If our measurement of cosmic expansion are being systematically biased by the structure of the web around us, then what looks like acceleration caused by dark energy might be partly or entirely an artifact of the voids themselves. This remains a hypothesis. It is not accepted consensus. The dark energy hypothesis has much stronger observational support from multiple independent lines of evidence. But the mere fact that researchers are seriously exploring this possibility tells you something important. Voids are no longer just the empty spaces between interesting things. They have become, in the eyes of some of the best cosmologists working today, one of the most important keys to understanding the universe. Summary and the open question. Let's take stock of where we are. We started with a group of astronomers mapping galaxies in 1981, who found a hole in the universe that was not supposed to be as large as it was. That hole, the Boötes Void, is approximately 330 million light-years across, sits 700 million light-years from Earth, and contains only about 60 known galaxies in a volume that should, by the universe's average density, contain around 2,000. We then step back to understand where voids come from. Tiny quantum fluctuations in the early universe, amplified by gravity over billions of years into the vast structure we call the cosmic web, a foam of filaments and walls and nodes surrounding empty bubbles, with the bubbles, the voids, occupy between 70 and 80% of the universe's total volume. We learn that voids are not as simple as they appear. They contain isolated galaxies with their own distinct evolutionary histories. They carry the irreducible energy of the quantum vacuum. They may be biasing our measurements of the universe's expansion rate. And one of the largest known voids, the KBC void, may contain, at its approximate center, our own Milky Way galaxy and every civilization and telescope and observation we have ever made. The universe, it turns out, has arranged itself so that most of its volume contains almost nothing. And from inside that almost nothing, we have somehow managed to figure out quite a lot. But there's a question that naturally arises from everything we have covered tonight, one that makes the story considerably stranger. We have talked about what voids look like from outside, from the cosmic web's perspective. We have talked about the galaxies that survived inside them. We have talked about vacuum energy and Hubble tensions. But we have not yet asked what is happening inside the void at the deepest level. Not in the quantum sense, in the structural sense. Because it turns out that voids are not featureless spheres. They have interiors. They are what some researchers describe as a substructure. Smaller voids nested inside larger ones, tenuous filaments threading to the dark interior. The ghost of a smaller scale web running through the emptiness. The cosmic web does not simply stop at the edge of a void. It whispers very faintly even inside it. And there is a growing body of evidence suggesting that this interior structure of voids carries information about the nature of dark energy, about the mass of neutrinos, about the precise geometry of the universe, that we cannot easily extract from the filaments and clusters alone. Which brings us to the question we will take with us into part 2. If voids are not truly empty, if they have structure, subvoids, quantum energy, and connections to the deepest unsolved problems in cosmology, then what exactly is hiding inside them? And what will we find when we finally look closely enough? In part 1, we establish the shape of the universe's emptiness. We talk about the cosmic web, that vast, foam-like architecture of filaments and walls and nodes, with enormous voids occupying the spaces between them. We saw how the Boötes Void, discovered almost by accident in 1981, stretches 330 million light-years across and contains only around 60 known galaxies where there should be 2,000. We learned that voids collectively account for somewhere between 70 and 80% of the universe's total volume. And we ended with a question. If voids are not truly empty, if they contain structure, isolated galaxies, quantum energy, and clues to some of the biggest unsolved problems in physics, what exactly is hiding inside them? Tonight, we go inside. We are going to look at the strange, slow lives of the galaxies that were left behind when matter drained away into filaments. We are going to follow ancient light as it crosses a supervoid and arrives at our telescopes, carrying the imprint of everything it passed through. We are going to visit one of the largest confirmed voids in the observable universe, a structure nearly 2 billion light-years wide, and examine what it is doing to the oldest light in the cosmos. And we are going to spend some time with a particularly unsettling idea, the possibility that the cold spot on the oldest map of the universe might be a scar left by the void we are about to describe. Let us begin with the survivors, the galaxies that were left behind. When you empty a room, You do not always get completely clean. You sweep most of the dust into the corners, most of the furniture out the door, but a few things remain. Something heavy that was too difficult to move, a chair somebody forgot, a picture on the wall that everybody walked past and never quite decided to take. Voids are like that. They are not completely empty, and the galaxies that remain inside them are, in a quiet way, among the most scientifically interesting objects in the universe. For most of the history of exogalactic astronomy, void galaxies were treated as little more than statistical anomalies. The noise and the data, the few objects that happened to sit in the wrong place when the cosmic web was assembling itself. They were mostly ignored in favor of the spectacular clusters and superclusters, where galaxies crowd together, interact, merge, and spark into furious bursts of star formation. But over the last few decades, a growing body of research has revealed that void galaxies are not just leftovers. They are a separate class of object, shaped by the extreme environment of the void in ways that tell us things about galaxy formation that we cannot learn anywhere else. The differences begin with something as basic as color. Galaxies and the dense filaments and clusters of the cosmic web tend to come in two broad flavors. There are red, elliptical galaxies, massive, old. Their star formation largely exhausted billions of years ago, glow with the warm red light of aging stars. And there are blue spiral galaxies, actively forming new stars, shaped like Catherine wheels of gas in young blue suns. In the dense environments of clusters, galaxies interact with each other constantly. They merge. They strip gas from each other through gravitational harassment. They age quickly, run through their fuel, and redden. In a void, things are different. Void galaxies, across numerous surveys and studies, tend to be bluer than their counterparts in denser environments. They tend to be less massive. They tend to have later morphologies, more disk-like, more spiral, retaining the structure of actively star-forming systems. They have higher current rates of star formation relative to their mass. But here is the key nuance established by observational work published in Nature in 2023 by Dominguez Gomez and colleagues from the Cavity Project. The Kähler-Alto Void Integral Field Treasury Survey. While void galaxies currently form stars at a higher rate relative to their mass, their overall star formation histories have been substantially slower. They assembled half of their total stellar mass later than galaxies in denser environments. They have not formed more stars in total. They have formed them more gradually, spread over a longer period of time. It is a kind of cosmic patience. In the crowded universe of filaments and clusters, galaxies experience the equivalent of a fast-moving city. Constant interactions, mergers, rapid evolution, quick burning through their fuel. In a void, with few neighbors and little gravitational interference, a galaxy can evolve at its own pace. Slowly, steadily, the gas it needs to form stars accumulates gently, not in violent mergers, but through slow accretion from the sparse intergalactic medium around it. A 2026 paper published in Astronomy and Astrophysics studied the molecular gas content of a galaxy called CG910, located inside the Boötes Void itself, one of the isolated galaxies we described in Part 1. The researchers found that void galaxies in general are gas-rich, with large reservoirs of the hydrogen that fuel star formation, but that this gas is assembled slowly with fewer disturbances. The picture that emerges is of galaxies living in a kind of suspended development, not stunted, not failed, but simply living on a different time scale, like a tree growing in thin soil, smaller than the ones in the valley, but still very much alive, and in some ways more independent. Dark matter simulations add another layer. Research using the illustrious TNG simulation suite, one of the most detailed computational models of galaxy formation available, found that void galaxies experience approximately the same number of mergers over cosmic time as non-void galaxies, but those mergers happen later. The timing shifts, the void delays things, and in that delay, the galaxy retains a different character. Younger stellar populations, bluer light, more gas, more what astronomers associate with early-stage development. There is something almost poignant about this. In the deepest, emptiest corners of the universe, where matter became sparse and the flow of cosmic architecture passed by. The galaxies that were left behind became a kind of repository of early universe conditions. They are, in a very real sense, fossils, not dead but preserved, living slowly in a quiet corner while the rest of the universe rushed forward. In the future, as dark energy continues to drive the universe's expansion, even those few connections that void galaxies have to their sparse surroundings will weaken further. The flow of gas from the intergalactic medium will diminish. The already slow pace of development will slow further still. The void galaxies will eventually burn through whatever gas they have, form their last generation of stars, and fade into red silence. But that is billions of years away. For now, they are still blue, still slowly building themselves, still the quietest galaxies in a universe that is otherwise in constant motion. The inner structure, voids within voids. When we talk about the interior of a cosmic void, it is tempting to picture something simple, a sphere of near emptiness, its surface defined by a shell of filaments, its interior dark and featureless, smooth and still. The reality, as revealed by increasingly detailed galaxy surveys and computational simulations, is considerably more complex. Voids are not smooth on the inside. They have interior structure. And one of the most striking features of that interior structure is this. Voids contain smaller voids. This nesting quality, sometimes called a hierarchical structure of voids, is a natural consequence of the same physical processes that created the large voids in the first place. When matter drains away from an underdense region into the surrounding filaments, it does not drain uniformly. It drains preferentially from the denser subregions inside the void, leaving behind a pattern of smaller underdensities nested within the larger one. Over time, those smaller underdensities develop their own structure, tenuous mini-filaments, tiny concentrations of matter, and still smaller voids within them. Simulations consistently predict this hierarchical nesting. Surveys of real galaxy distributions confirm it observationally, though the small galaxies and faint filaments inside voids are difficult to detect because they are, by definition, sparse and faint. But the evidence is there. In a large void, look carefully enough, and you'll find a rough web of substructure, ghost filaments running to the dark interior, dwarf galaxies scattered along them, tiny clusters of their intersections, and the smallest void of all tucked into corners of the substructure. Dark matter simulations suggest that void interiors, while significantly below average density overall, are not uniformly empty. The central cores of voids tend to be the emptiest regions, dropping to roughly 10 to 20% of the cosmic mean density. The outer regions near the void's edges are less extreme, rising toward 30 to 40% of the mean. This gradient from sparse center to less sparse edge is one of the characteristic features of a void's density profile, and it carries information that cosmologists can use to test models of structure formation and dark energy. There is also, threading through all of this, something that deserves a mention because it is so easy to overlook: the warm-hot intergalactic medium, sometimes abbreviated as WEM. Even in the emptiest known regions of the universe, space is not a perfect vacuum. It contains an extraordinarily diffuse gas, far too thin to form stars or even to be easily detected, at temperatures ranging from roughly 100,000 to 10 million Kelvin. This gas, which is believed to contain a substantial fraction of all the ordinary atomic matter in the universe, fills the spaces both inside filaments and more thinly inside voids. In a void, this gas is spread almost incomprehensibly thin. Research has suggested that the core of a large void might contain as little as 1 hydrogen atom per 5 cubic meters of space. To put that in context, the air in a room where you are sitting contains roughly 10 to the power of 25 molecules per cubic meter. A void's core contains, in the same volume, essentially nothing, not absolute vacuum, but so close to it that the distinction matters only at the level of very sensitive physics. It is inside this near vacuum that the quantum vacuum energy we discussed in Part 1 most clearly dominates, with almost no ordinary matter present to compete with it. The irreducible energy of empty space, the ground state of the quantum fields that permeate all of existence, becomes a dominant form of energy in the local environment. Voids, in this sense, are the universe's purest samples of dark energy's territory. Ancient light and the mark of the void. Now let us shift perspective entirely. Instead of looking at what is inside the void from the outside, let us follow something that travels through the void from end to end. Light. Not just any light. The oldest light in the universe. Approximately 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before this moment, the universe had been an opaque plasma. Photons could not travel freely because they were constantly scattering off charged particles. With the formation of neutral atoms, the plasma cleared. The photons that had been trapped in it were suddenly free to travel in straight lines, and they have been traveling ever since. For 13.8 billion years, carrying the pattern of the early universe embedded in their distribution. We detect those photons today as the cosmic microwave background, the CMB. It is the most ancient light we can observe. It comes from every direction in the sky in nearly equal amounts, at a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. And when we map it with extraordinary precision, as the Planck satellite has done, we see that it is not perfectly uniform. There are tiny fluctuations, temperature differences of roughly 1 part in 100,000, that encode the density variations of the early universe. Most of those fluctuations were set in the first fractions of a second after the Big Bang, and they have been traveling with the photons ever since. But the CMB photons are not untouched by the 13.8 billion year journey they made to reach us. Along the way, they passed through the evolving structure of the universe, through filaments, through clusters, and through voids. And each of those structures left a subtle imprint on them. This imprint has a name, the integrated Sachs-Wolf effect. And to understand it, we need to think about what happens when a photon crosses a cosmic void. Picture a photon, a particle of light, traveling across the universe toward us. It approaches the edge of a large void. To enter the void, the photon has to climb what physicists call a gravitational potential hill, a region where matter density is lower than the surroundings, so the gravitational potential is slightly higher. Climbing this hill costs the photon a small amount of energy, causing it to redshift slightly. It becomes ever so slightly cooler. Inside the void, the photon travels through the sparse interior. Eventually, it reaches the other side. Now it descends the potential hill on the far edge. Descending gains energy. The photon blue shifts slightly, recovering its lost energy. In a static universe, these two effects would cancel exactly. The energy lost climbing and would equal the energy gained descending out. Net result, no change. But we do not live in a static universe. We live in one that is expanding, and more than that, one in which the expansion is accelerating, driven by dark energy. While the photon was crossing the void itself was expanding, stretching outward under the influence of dark energy. The gravitational potential hill on the far side of the void, when the photon reaches it to descend, is shallower than the hill it climbed on entry, because the void has expanded and the matter at its edges has spread further apart. The result is that the photon gains less energy descending than it lost climbing. There is a net energy loss. The photon arrives at our telescopes slightly cooler than it would have been had it not crossed the void. This is the integrated Sachs-Wolf effect. A void leaves its mark on ancient light, not through any dramatic interaction, but through the quiet interplay between an expanding universe and the shape of the gravitational landscape, measured statistically by comparing the temperature map of the CMB with the distribution of large voids identified in galaxy surveys. This effect is one of the independent lines of evidence for dark energy. Without the accelerating expansion driven by dark energy, the effect would not exist. The gains and losses would cancel. Its detection is a confirmation that something is driving that acceleration. And now the effect takes on an extraordinary dimension, because when we look at the CMB map, the most precisely measured snapshot of the early universe, there is one feature that does not quite fit. a feature that has generated more debate and speculation than almost anything else in modern cosmology. A region of sky that is simply colder than it should be, the cold spot. It is located in the southern sky, in the direction of the constellation Eridanus. Astronomers call it, straightforwardly, the CMB cold spot. On the CMB temperature map, it appears as a roughly circular region about 10 degrees across, roughly 20 times the apparent diameter of the full moon on the sky, where the temperature of the background radiation is measurably lower than the surrounding area. The temperature difference is about 70 microkelvin. That is 70 millionths of a degree on any absolute temperature scale. It is a number so small as to be almost meaningless. But in the context of the CMB, where temperature fluctuations typically measure only 1 part in 100,000, a 70 microkelvin deviation is significant, statistically anomalous enough that when the Planck satellite data was analyzed, the cold spot emerged as one of the features of the CMB that the standard model of cosmology does not straightforwardly predict. It has not been explained away. It is still there, still anomalous, still being studied. There are several proposed explanations for the cold spot. Let's be precise about what each of them is, and what the current state of evidence says about each. The first and simplest class of explanation is statistical. The cold spot might be a rare but not impossible fluctuation, a region that happened to be slightly colder in the early universe, consistent with the standard model, but simply an outlier in the distribution. The universe is large and rare events occur. On this view, the cold spot is not a sign of anything unusual. It is just the cosmos being itself, producing extremes at the tails of its distributions. This explanation cannot be ruled out. Whether the cold spot is improbable enough to require a special explanation, or just unusual enough to be notable but not inexplicable, is itself a matter of ongoing debate among statisticians and cosmologists. The second class of explanation involves foreground structures, things between us and the CMB that could be cooling the photons passing through them. This is where voids become directly relevant. In 2015, a team of astronomers identified a supervoid in the direction of the cold spot, an enormous underdense region in the constellation Eridanus. Subsequent surveys confirmed and refined the detection. Using data from the Dark Energy Survey, researchers confirmed in 2022 that the Eridanus Supervoid is a real structure, extending roughly 1.8 billion light-years across, centered about 2 to 3 billion light-years from Earth, and containing approximately 20 to 30% less matter than the cosmic average. It is the most prominent large-scale underdensity in the DES dataset. Its existence is not in doubt. The question is whether it can explain the cold spot. Here's what the evidence actually says, stated carefully. The Eridanus Supervoid is real, and it sits in the direction of the cold spot. A void of that size and depth would, via the integrated Sachs-Wolf effect we described earlier, leave a cold imprint on the CMB photons that pass through it. When researchers calculate how large that imprint should be, assuming the standard lambda CDM cosmological model, they find that the supervoid can account for roughly 10 to 20% of the observed temperature depression of the cold spot. Not all of it. Somewhere between 80 and 90% of the cold spot's anomalous coldness remains unaccounted for by the Eridanus Supervoid alone. Under the standard model, there are a few distinct responses to this gap in the scientific community. One response is to accept it as consistent with the statistical explanation. The Eridanus Supervoid contributes a small but real component of the coldness, and the rest is simply a statistical fluctuation. On this reading, the alignment between the supervoid and the cold spot is a coincidence of rare, but not impossible structures. A second response notes something interesting and potentially significant. Observations of other large supervoids elsewhere in the sky have shown integrated Sachs-Wolf imprints roughly 5 times stronger than what the standard model predicts. If that ratio held for the Eridanus Supervoid, it would explain much more of the cold spot. Some researchers have proposed that the standard model's prediction for the ISW effect from large voids may be systematically underestimated, though this idea does not yet have consensus support. A third class of explanations for the cold spot remains exotic and has much weaker observational support. Some researchers have proposed that the cold spot might be the imprint of a collision between our universe and a neighboring bubble universe, a consequence of eternal inflation, in which our universe is just one of many inflated bubbles, and a collision would leave a cold bruise on the CMB. This is a genuine theoretical possibility within certain inflationary models, but it currently lacks observational confirmation and is considered speculative by the mainstream of the cosmological community. It is a hypothesis some researchers take seriously, not a theory with established evidence. The cold spot is not explained. Its current status is a real feature confirmed across multiple datasets, inconsistently predicted by the standard model, with a real supervoid in the right direction, but of insufficient apparent effect to account for all of it, and with multiple competing hypotheses that are still actively being evaluated. Future surveys, including data from ESA's Euclid mission now operating in space, are expected to provide more precise measurements of the Eridanus Supervoid structure and the ISW signal it produces, which may help narrow down the possibilities. For our purposes tonight, the cold spot is a universe writing something on its own oldest portrait, a mark whose full meaning we cannot yet read: the photon's long journey. Let us return to the photon crossing the void, because there is one more dimension to this story that is worth sitting with before we move on. The Eridanus Supervoid is approximately 1.8 billion light-years across. A photon of light crossing it from one side to the other would spend 1.8 billion years in transit. That is more than a third of the current age of the universe. During that crossing, our sun had not yet formed. During that crossing, the Earth did not exist. During that crossing, all of the geology of our planet, all of the evolution of life from the first single-celled organisms to every dinosaur and tree and human being who has ever lived, none of it had happened yet when those photons entered the void. And when they emerged at the far side, the Earth was still hundreds of millions of years away from forming its first multicellular life. And those photons are the ones that then travel for another 2 billion years to reach our telescopes, carrying on their wavelengths the memory of having crossed that void. The universe is in the habit of writing its own history in the light that crosses it. Every photon that reaches our detectors is a kind of message, carrying the accumulated record of everything it passed through on its way here. The CMB cold spot may be one of those messages. Its full meaning is still unclear, but the Eridanus Supervoid, sitting between us and that cold patch of sky, is one of the largest confirmed structures of emptiness in the observable universe, real, measured, and strange. Home in the void, the KBC question. There is one more piece of the story that we deferred from part one, and it is the most personally relevant of everything we will discuss tonight. In part one, we introduced the KBC void, the proposed large underdensity centered approximately on the Milky Way, roughly 2 billion light-years in diameter, with matter density somewhere between 15 and 50% below the cosmic average. We noted that its existence is scientifically contested. Some analyses support it, some find a smaller effect, and the question of its exact size and depth is still being measured. Since that initial description, the evidence has continued to develop. A 2025 paper by Eridanus Supervoid and Vasilios Kaliitsidis, published in the monthly notices of the Royal Astronomical Society, examined baryon acoustic oscillation measurements taken over roughly 2 decades and evaluated whether they were consistent with the local void hypothesis. Their analysis found that a local underdensity is a plausible contributor to the Hubble tension, the persistent discrepancy between local and early universe measurements of the universe's expansion rate. Bannock had previously calculated that the KBC void, if it exists at the depth and scale originally proposed, could raise the locally measured Hubble constant by approximately 11% relative to the global average, which is approximately the size of the Hubble tension. We should be careful here. The local void hypothesis is one of several competing explanations for the Hubble tension, none of which has achieved consensus. Some researchers find the void insufficient to explain the tension. The tension itself may have multiple contributing factors, and the standard cosmological model, lambda CDM, predicts that voids as large as a proposed KBC void are themselves near the edge of what is plausible, though not impossible. What is agreed upon is this: There is some degree of local underdensity. The region immediately around our galaxy and extending for some distance in all directions appears to have somewhat fewer galaxies and somewhat less matter than the cosmic average. The debate is about how large and how deep that underdensity is, and whether it is large enough and deep enough to have measurable effects on the cosmological constants we derive from local observations. If the KBC void is real at the scale proposed, then every Hubble constant measurement made from the surface of the Earth, from our position inside the void, has been slightly biased by our location. We would be doing astronomy from inside a hole, and our rulers would be stretched by the local expansion of that hole. The maps we have drawn of the universe's expansion rate would need to be corrected. This is not a crisis. It is not a sign that cosmology has gone wrong. It is a reminder that where you stand matters, even in science, even in measurements of the entire universe. The universe does not have a center, and it does not have a preferred observer, but different positions within it offer different views, and some views are less representative than others. If we live in a void, our view may be one of those. What the emptiness reveals. We have now spent considerable time inside the void, looking at its contents from multiple angles. Let us take a moment to collect what we have found. Inside the voids, there are survivor galaxies, isolated, slowly evolving, gas-rich blue, retaining the character of early-stage development while the rest of the universe aged around them. These galaxies are not failures. They are archives. They preserve conditions and processes that have been disrupted or destroyed in the dense environment of clusters, and they offer astronomers a way to study galaxy evolution without the noise of environmental interference. Inside the voids, there is a ghost architecture. Subvoids nested within larger voids, tenuous filaments threading through the interior, a whisper of the cosmic web that extends even into the emptiest regions. The void has texture. It has hierarchy. It is not nothing. It is a lesser version of the something that surrounds it. Inside the voids, ancient photons have been gently cooled by the integrated Sachs-Wolf effect, carrying the record of their crossing in the form of slight temperature shifts that our instruments can now detect and measure. The CMB itself, the oldest light in the universe, has been shaped by every void it passed through, and those shapings are one of our tools for studying dark energy. And above all, inside one particular void, the one we may be living in, is us, observers whose location in the universe may be less typical than we assumed. Astronomers who have been measuring the cosmos from inside an underdense bubble, and who may need to account for that bubble when interpreting the numbers they derive. The void is not empty of significance. It is full of it. Summary and the open question. Let us close part 2 by bringing together what we have learned. The inside of a cosmic void is not featureless darkness. It contains isolated galaxies evolving on their own quiet timescales, bluer, younger in character, slower to build their stars, more patient than the frenetic galaxies of dense clusters. It contains a nested hierarchy of smaller voids and faint subfilaments that extends the logic of the cosmic web even into its emptiest reaches. It contains the thinnest gas imaginable, near vacuum, near perfect, perhaps approaching 1 hydrogen atom per 5 cubic meters at the core, in which the quantum vacuum energy that underlies dark energy goes essentially unopposed. And it contains the imprints left on ancient light. The Eridanus Supervoid, one of the largest confirmed underdensities in the observable universe, nearly 2 billion light-years across, sits between us and a feature of the CMB that has puzzled cosmologists for 2 decades. The cold spot, a patch of sky 70 microkelvin colder than it should be. The supervoid has confirmed its reality through multiple independent observations, including gravitational lensing maps from the Dark Energy Survey. It contributes a measurable cold imprint to the CMB via the integrated Sachs-Wolf effect. But under the standard cosmological model, it accounts for only 10 to 20% of the cold spot's anomalous temperature. The rest remains unexplained. Multiple hypotheses exist. Statistical fluctuation, underestimated ISW effects, exotic explanations involving bubble universes, but none has been confirmed and none has been ruled out. The voids are speaking. We are still learning how to listen. And that raises the question we will take into our final chapter. We have seen what voids contain. We have seen what they do to the light that crosses them. We have seen how they may be biasing our measurements of the universe's expansion and how they may hold clues to dark energy's true nature. But we have not yet asked what happens to voids as the universe continues to evolve. What is their future? What are they becoming? The universe is expanding. The expansion is accelerating. The filaments of the cosmic web are being stretched and thinned. The great clusters of galaxies are being pushed apart. Matter that was already concentrated is concentrating further, and the voids between structures are growing larger. The emptiness, in other words, is winning. What does it look like when the void inherits the universe? Before we went inside the emptiness, we met the slow blue, gas-rich galaxies that were left behind when matter drained toward the filaments. We found that voids are not smooth, that they contain a ghost hierarchy of smaller voids and faint subfilaments, a whisper of the cosmic web extending even into its emptiest reaches. We followed the oldest light in the universe as it crossed the Eridanus Supervoid, and we sat with the unresolved mystery of the CMB cold spot. And we ended with our own possible address, a galaxy that may sit near the center of an underdense region nearly 2 billion light-years across, looking out at the universe from inside a hole. Tonight, we close the story. We are going to look at what voids are doing for science right now, how they have become, in the last decade, one of the sharpest tools cosmologists have for testing the fundamental nature of the universe. We're going to look forward in time, billions and trillions of years, and ask what becomes of these vast empty regions as the universe continues to expand. And we are going to end with something different, not a fact, not a measurement, but a question that sits at the edge of physics and philosophy. What does it mean that emptiness of all things may be the condition that allows everything else to exist? Let's begin with the present. Voids as instruments. For most of the 20th century, voids were treated the way empty rooms are treated in a museum, as the spaces between exhibits. Interesting only insofar as they set off the object around them. Nobody studied the empty room itself. That has changed. In the last 15 years or so, voids have become exhibits in their own right. Not because something is hiding inside them, but because their size, shape, and number turn out to be extraordinarily sensitive to the deep parameters of the universe. The amount and behavior of dark energy, the properties of dark matter, and even the massive neutrino, one of the lightest and most elusive particles known to exist. Here's the basic idea. The growth of a void over cosmic time is a tug-of-war between two things. On one side, gravity, which pulls matter out of underdense regions and into the surrounding filaments, making the void emptier and, in a sense, larger. On the other side, the expansion of the universe itself, which stretches every distance, including the distances inside a void, and which, if dark energy is doing what current models say it is doing, is accelerating, because voids are dominated by this competition in a relatively clean way. There is little matter inside them to complicate the picture with its own gravity. They respond to changes in the expansion rate and the strength of gravity more directly than dense regions do. A cluster of galaxies is a noisy, complicated system, full of its own internal physics, mergers, gas dynamics, feedback from supermassive black holes. A void, by comparison, is almost a controlled experiment. Change the properties of dark energy even slightly, and the population of voids, their sizes, their abundance, the way their edges are shaped, shifts in predictable ways. This is why voids have become central to a new generation of galaxy surveys. The Dark Energy Spectroscopic Instrument, DESI, which began its main survey in 2021 and is mapping tens of millions of galaxies and quasars across roughly a third of the sky, includes void statistics as one of its core science goals. The Euclid Space Telescope, launched by the European Space Agency in 2023 and now conducting its survey, is designed in part to map the size and distribution of voids across a large fraction of the observable universe, specifically to test models of dark energy and gravity. Early results from these and earlier surveys, including the Baryon Oscillation Spectroscopic Survey, have already used the distribution of voids to place independent constraints on cosmological parameters. constraints that are broadly consistent with the standard lambda CDM model, while also being precise enough to start testing for small departures from it. There is also a more exotic application. Some of the proposed alternatives to dark energy involve modifications to general relativity itself. Theories in which gravity behaves slightly differently on the largest scales than Einstein's equations predict, in a way that can mimic the effect of dark energy without requiring a new form of energy at all. These modified gravity theories tend to make very specific predictions about voids, because in a true vacuum, with almost no matter present, any deviation from standard gravity would have nowhere to hide. Several research groups have proposed using the interiors of voids as a kind of clean laboratory to test for these deviations by looking at how galaxies move and how light bends as it passes through the emptiest regions of space. This is an active area of research, not a settled result. No confirmed deviation from standard gravity has been found inside voids, but illustrates how seriously the emptiness is now being taken. And then there is the neutrino. Neutrinos are produced in vast numbers by the Big Bang, by stars, and by radioactive decay, and they have mass, though an extremely small one, still not precisely measured. Because neutrinos move at close to the speed of light and barely interact with anything, they tend to smooth out small-scale structure in the universe, including the structure of voids. The more massive neutrinos are, the more they smooth things out. This means that the fine details of void shapes and sizes, particularly the smallest voids, carry information about the total mass of all neutrino species combined, information that is very difficult to obtain by any other method. Current cosmological surveys, including those that use voids, have placed an upper limit on the sum of neutrino masses of roughly 0.12 electron volts, a number so small it is hard compared to anything in everyday experience, but one that represents one of the tightest constraints we have on these particles, and one that void statistics contribute to directly. In other words, the empty room is no longer just a space between the exhibits. The empty room has become one of the most precise instruments in the building, the future of the voids. Now let us look forward. The universe today is roughly 13.8 billion years old. The structures we've been describing, the cosmic web, the filaments, the clusters, the voids, are still actively evolving. The voids are still growing. The filaments are still in places, funneling gas into galaxies and fueling new star formation. The universe, in a sense, is still under construction, but the construction has a direction, and that direction is set by dark energy. According to the standard lambda CDM model, our current best framework, supported by multiple independent lines of evidence, including the CMB, the large-scale structure of galaxies, and the brightness of distant supernovae, the expansion of the universe is not just continuing, it is accelerating. And unlike the expansion driven by the initial conditions of the Big Bang, which would naturally slow down over time due to the gravitational pull of all the matter in the universe, this acceleration appears to be driven by something else. Dark energy, the same component that, as we discussed in Part 1, may be most directly expressed inside the voids themselves. If dark energy continues to behave the way our simplest models predict, as a constant energy density associated with empty space itself, often called a cosmological constant, then the long-term future of the universe has been worked out in broad strokes by cosmologists, and it is a future in which the voids do not just persist. They take over everything. Here is roughly how that future unfolds, according to current models. And it is worth being clear that current models is the operative phrase. These are extrapolations of well-supported physics over timescales so vast that direct confirmation is, by definition, impossible. They represent the best understanding available today, not a prophecy. Over the next tens of billions of years, the accelerating expansion will continue to stretch the distances between galaxy clusters and superclusters, structures that are not gravitationally bound to each other. That is, structures where the mutual gravitational pull is too weak to overcome the expansion will drift apart at ever-increasing rates. The filament of the cosmic web, which today connect galaxy clusters across hundreds of millions of light years, will stretch and thin. Galaxies that are gravitationally bound to each other, like the Milky Way and the Andromeda Galaxy, which are expected to merge in the coming billions of years, will remain together, forming larger but more isolated islands. But the connections between these islands, the filaments, the bridges of the cosmic web, will gradually fade as the matter within them is pulled apart by the expansion of space. In effect, the cosmic web will unravel. The walls and filaments that separate today's voids from each other will stretch until they are no longer distinct from the voids themselves. The distinction between inside a void and outside a void will become less and less meaningful because the entire universe will be approaching the density of what is today a void's interior, on timescales of roughly 100 billion years. Still a small fraction of the timescales cosmologists sometimes work with, but vastly longer than the current age of the universe. Models suggest that the accelerating expansion will have carried every galaxy cluster not gravitationally bound to our own local group beyond the cosmic horizon, the distance beyond which light can never reach us again, because the space between us and that object is expanding faster than light can cross it. From the perspective of any surviving observer in any surviving galaxy, the rest of the universe will appear to disappear, not explosively, but by quietly receding past the point of no return, one galaxy at a time, until the sky outside their own galactic island is empty. At that point, in a sense, the voids will have won completely, not because anything dramatic happened to the matter in the universe. Stars will still be forming and dying inside the surviving galactic islands for a very long time after this, but because the large-scale structure, the cosmic web of filaments and walls and nodes that we described in Part 1, will have ceased to exist as a connected structure. What remains will be isolated islands of matter, drifting in a universe that is, for all practical purposes, one continuous void. Some cosmologists describe this end state using a term borrowed from a much older idea, the heat death of the universe, or more precisely, in this dark energy-dominated scenario, an approach toward what is called a de Sitter universe, a state named after the Dutch astronomer Willem de Sitter, who in the early 20th century described a model of an empty, accelerating universe as a mathematical solution to Einstein's equations, decades before anyone thought it might describe our actual future. In a de Sitter universe, every region of space is, in the long run, dominated by the energy of the vacuum itself, the same vacuum energy we discuss inside today's voids, with matter so diluted by expansion that it becomes a negligible component. It is worth being precise about the timescales here, because they are almost beyond intuition. The transition we just described, the unraveling of the cosmic web, the disappearance of other galaxies beyond the horizon, plays out over roughly tens to a few 100 billion years. But the stars themselves will burn for far longer. The smallest, dimmest stars in the universe, red dwarfs, the most common type of star, are expected to continue fusing hydrogen for trillions of years, far outliving the sun many times over. Star formation in general, fueled by the dwindling supply of coal gas, is expected to taper off and largely cease somewhere in the range of 100 trillion years from now, an era sometimes called the Stelliferous Era's end. After that, on timescales of quadrillions of years and beyond, numbers that exist mostly as exponents in equations rather than as anything anyone could meaningfully picture. Even the longest-lived stars will exhaust their fuel, and the universe will enter eras dominated first by dead stellar remnants, and eventually, on truly staggering timescales, by the slow evaporation of even those remnants and the dilution of all matter into an increasingly void-like cosmos. We should be careful, again, about how much weight to place on these extrapolations. They depend on dark energy continuing to behave as a true cosmological constant, an assumption that is consistent with all current observations, but not proven beyond all doubt. Some researchers have explored models of evolving dark energy, in which the dark energy density changes over cosmic time rather than remaining constant. If such models turn out to be correct, the long-term future could look different, potentially involving either a slower approach to a void-dominated state, or, in some more exotic and far less favored scenarios, even a future contraction of the universe. As of now, the evolving dark energy models remain a minority position, actively investigated but not preferred over the simple cosmological constant. What can be said with confidence is this: Under our current best supported model, the trajectory points toward an ever emptier universe, toward the voids in some sense, become the default state of everything. The architecture we described in Part 1, the foam, the sponge, the cosmic web of filaments and nodes, is not a permanent feature of the universe. It is a phase, a long phase, by any human measure, lasting many tens of billions of years more at least, but a phase nonetheless, bounded on one side by the dense early universe before the web had time to form, and bounded on the other side by an emptier universe in which the web has unraveled. We are living right now, somewhere in the middle of that phase, at a moment when the cosmic web is at or near its most elaborate, most richly structured state. The voids around us are still relatively young, still actively growing, still bordered by filaments rich with galaxies. In the very deep future, the voids will not need to grow anymore. They will simply be what is left, the condition for everything. We want to end with something a little different, not a new fact, but a way of looking at everything we have covered across these three parts. Throughout this series, we have treated voids as a kind of absence, a lack, the places where matter is not. And by most definitions, that is exactly what they are. Regions of below-average density, places where the great structures of the cosmic web thinned out and emptied over billions of years. But there's another way to look at the relationship between voids and structure, one that does not change any of the science we had discussed, but reframes it. Consider this. Without the voids, there would be no filaments. Without the regions where matter flowed away, there would be nowhere for the matter to flow to, the dense structures we find so compelling. The galaxies, the clusters, the glittering nodes of the cosmic web, where most of the light in the universe is produced, exist as dense structures only because there are also regions that are not dense. The contrast is not incidental to the structure. The contrast is the structure. This is not a mystical claim. It follows directly from the physics we described in Part 1. The same gravitational process that pulled matter into filaments and clusters is the process that emptied the voids. They are not two separate phenomena that happen to coexist. They are two descriptions of a single process, viewed from two different vantage points. Asking which one is real and which one is the absence is a bit like asking whether sculpture is defined by the marble that remains or the marble that was removed. The question does not quite make sense, because the final shape depends on both. There is a similar idea in the way physicists think about emptiness at the smallest scales. The quantum vacuum we discussed in Part 1, the sea of fluctuating fields that underlies all of existence, with its irreducible ground state energy. In quantum field theory, particles are often described as excitations of an underlying field, ripples on a surface that is in its undisturbed state, what we call empty space. The vacuum, in this picture, is not nothing. It is the canvas. The particles, the stars, the galaxies, all of it is structure imposed on top of that canvas. Without the canvas, there is nothing for the structure to be made of or to exist within. Push this idea further, and a thought emerges that several cosmologists and physicists have voiced over the years in different forms. Emptiness, at every scale we have examined, from the quantum vacuum to the great voids of the cosmic web, is not simply the leftover space after the interesting things are accounted for. It may be closer to a precondition, the background against which everything else is defined. Without something like a void, a region of lower density, lower energy, less stuff, there would be nothing for the higher density regions to stand out against, nothing to define them as structures at all. We want to be careful here, because this is a point in the story where it becomes easy to drift from physics into something that sounds profound but says less than it appears to. So let us be precise about what is established and what is interpretation. What is established? The universe's large-scale structure is a single interconnected system in which dense regions and underdense regions are two aspects of the same gravitational history, governed by the same physical laws, traceable back to the same tiny fluctuations in the early universe. Voids are not a separate category of object bolted onto an otherwise full universe. They are the necessary complement to everything we call full. What is interpretation? Whether this fact carries some deeper meaning, whether it tells us something about the nature of existence itself, about why there's a universe with structure in it rather than a uniform, featureless one, is a question that sits outside the boundaries of what physics, as a discipline, can currently answer. Some physicists and philosophers find this kind of question worth asking. Others consider it outside the scope of science altogether, a question of language and framing rather than a fact. Both positions are reasonable, and the choice between them is, in the end, a matter of temperament as much as evidence. What we can say, leaving the philosophy aside, is this: the story of the universe is not a story about things appearing in an empty stage. It is a story about a stage and its contents differentiating from each other together over 13.8 billion years. Gravity pulling matter into filaments here, and by the same motion, leaving space behind there. The voids are not what is missing from the universe. They are one half of how the universe became the shape it is. Closing. We began this series with an accidental discovery in 1981, a hole in the sky that nobody expected, found by astronomers who were simply trying to map galaxies, and instead found an absence so large it seemed to violate the rules. We trace that absence back to its origins in the quantum fluctuations of the earliest universe, and forward through billions of years of gravitational sculpting into the great cosmic web of filaments and walls and nodes that defines the architecture of everything we can see. We went inside that emptiness and found it was not empty after all. Not in the way the word suggests. We found galaxies living on their own slow timescales, fossils of an earlier mode of existence. We found a ghost hierarchy of smaller voids nested within larger ones. We found a quantum vacuum, asserting itself most clearly in the places where matter had thinned out enough to stop competing with it. We followed ancient light across one of these vast structures and found it carrying, in its temperature, the faint and still partially unexplained imprint of that crossing. And we considered a possibility, still debated, still being tested by current and future surveys, that we ourselves live inside one of these structures, that the address of every person who has ever lived, every measurement ever taken, every theory ever proposed, might be somewhere inside a void looking out. Tonight, we looked forward and found that the voids are not a temporary feature of a young universe. They are on the timescales that govern the deep future, where everything is going. The filaments will fade, the clusters will drift apart. The richly connected web we see tonight, when we look at the deepest galaxy surveys ever made, is, on a long enough timeline, a passing arrangement. The emptiness was here before the structure formed, in the smooth and nearly uniform plasma of the early universe. And the emptiness, in some form, is what the structure is slowly returning to. Between those two kinds of emptiness, the smooth beginning and the diffuse end, lies everything. Every star that has ever shone, every planet that has ever formed, everyone who has ever looked up at a night sky and wondered what it meant. We live, for now, in the interesting part, in the part where the contrast between full and empty is sharp enough to produce galaxies and stars, and the kind of complexity that can build telescopes and ask questions about voids in the first place. The great voids are not the absence of a story. They are the space the story needed in order to be told.